Hi, Paul from Tite-Spot Welders. This is our fourth and final segment. I'm going to teach you some things about electricity and how to measure and what it looks like. I'm an oscilloscope here, I've got some meters here. And what we're going to do is, very briefly, this is what we're going to do. I'm going to show you that the control does this. When we turn the power up and down on this thing, we're actually turning the voltage up and down. And if Kenny strokes in here on this meter, you can see that when I turn the power up, the lights come up and the voltage goes up. Now this meter here is reading what's called average voltage, and the accuracy is probably 3 to 5%. It's not bad. It's lousier when we use phase shifting, which is what we're using here to control the power. A much better meter is a meter like this. This is a true RMS meter. It has much better accuracy. One like this is real splendid. I mean, this is a $400 fluke meter. Those are real nice. And you can measure things much more accurately. Well, the other thing that we're going to do now, what we're going to do here is this is hooked up here, and we're going to measure the input voltage. The input voltage into the transformer. We're going to measure the input current into the transformer with a little clamp on that meter. You can see they just go like this. You've probably seen them. They have ones that plug into your voltometer different ways. Some of them are digital. This one's cheap. The accuracy is not tremendous, but it's in the neighborhood of 3%, so that's good enough. Okay, if I clamp this meter on here, all right, and then I read this voltage here, and then I'm going to read the output voltage here, this is what's going to happen. I've already written it down on the wall over here. And this is what the deal is. You have your input volt, which is 185 volts. Now you may think 185 volts, Paul, what kind of lousy building are you in? Well, we're in a building with 208 volt three-phase. And the input voltage today is only around 201 or 202 volts because it's a warm day in Wisconsin, everybody's running their air conditioners, you get low voltage. You got 240 volts in your building, you're going to find that this number is higher, which will make this number higher. But this is what happens. You have the input equals the output. Now there is some loss, so you're going to add it on the input side. And I'll explain that in a minute. My input voltage is 185. My input amperage is 150 amperes coming out of the wall right here. I got 150 amps coming out of this wall. Yeah, I've got it on a 50 amp breaker. You have to hold it there for about 5 seconds, you'll pop the breaker. We're using the surge part of the breaker, which is the part that if you had a 5 horsepower compressor, it would use the surge part. Alright, this is my output voltage, 6.36 volts, and that's measured right here at the transformer. Now, the other thing that we're going to do is you multiply this out and you get 27,750 watts. Now, let me explain what a watt is. If this is a 100-watt light bulb, that means that the power going into this transformer is equivalent to 277 100-watt light bulbs. That's how much power is going in here. 277 100-watt light bulbs. Now just think if you screwed 277 on, you flip the switch on it, I mean, you'd start to cook really quick because there's a lot of heat coming off. Well, that's the amount of power that we're going to shove into that weld. That's how it works. Now, you still have 6 volts on the output times the amperage. So if you divide both sides of the equation by 6.3, you're going to come out with your amperage, your calculated amperage, is 4,363 amperes. Okay? Now, the next thing that we're going to do here is I'm going to take and I'm going to measure the amperage. And we'll measure it with a device like this. Now this device will measure up to 8,000 amperes with a 0.1% accuracy. So this is an extremely accurate thing. It's basically, it's a transformer. There's iron in here and there's wire wrapped around it, and it's a transformer, and it's a very, very accurate device. This is another one. This one will measure up to 2,000 amperes. And I'm going to measure this amperage with my meter. I'm going to write that down over here, and this will give me my efficiency of the transformer, and then we'll know what our real number is. So I'll be right back in just a minute. I'm back now. I've now measured the amount of amperage. that this has. And according to this coil and this fluke digital 1 or 2% amperage meter, I have determined that we have 3,552 amperes of measured current coming out of the transformer. That gives us an efficiency of 81%. In other words, 19% of the power we got going in is wasted inside the transformer, and if you reach down here and you feel, oh, sure enough, that's starting to get warm. Oh, yeah, sure enough, that's starting to get warm. Sure enough, the iron gets warm. There's a loss in the iron, there's a loss in the primary, there's a loss in the secondary. It's all within the boundaries of the transformer, and you got a 19% loss. A 19% loss on the transformer this side is a real good transformer. Most transformers won't perform that well. All right, that's how you do that. Now, the reason I talk about this is because I've got some competitors out there who are spreading stuff that you ought to shovel up off the barn floor after the horses spent the night in the stall. And they're saying that they're making fantastic amounts of current. Now, I have a competitor who's claiming that he can make 20,000 amperes. Very simply, if he has a machine that's as efficient as mine at 81%, and we want to have 20,000, well, let me calculate that. We would have to have a lot more power going into there. What is that going to be? You're going to have over 5 times the power, and we are already drawing 150 amps out of the wall. That means out of the wall here, we're not going to be sucking 150 amps. We're going to be sucking over 900 amperes. And I don't believe a power cord anywhere near this size is going to be adequate for 900 amperes. You're going to have a power cord somewhere in the neighborhood of 3 ones, which would mean the wires are as big as your little finger. It just, people are making stuff up. I have another competitor out there who's talking about he has, capacitors in his machine. And these capacitors are going to store the energy or do something or other. Well, I don't know how he's going to store the energy because he's consuming the energy as he's creating it. So the capacitors don't do anything other than they flatten out the pulses. To store that much energy, if you were going to store it before you started to use it, you'd have to have a couple of 55-gallon drum-sized capacitors. Those would cost you probably, I don't even know, $40,000, $50,000 a piece. The price would be ridiculous. I suppose NASA uses them for something, or I don't know who would use those. I have no understanding of anybody who would use capacitors that big. If you go to your doctor's office and you go into the X-ray department, then you'll find ones that are about the size of a 10-gallon pail. And just ask them how much those cost, and you'd just be frightened with the price of those things. Anyway, that's how you measure the current and the voltage coming in. You measure the voltage going out, and you can calculate the amount of power and the amount of current that you can make. Now, there are other people out there who claim that they are very knowledgeable in this thing, and they write publications, and you've seen it in some of the magazines, and these guys, they write stuff. Some of the stuff that they write, they simply do not know what they're talking about. The way that we measure current and the standards that are being set up are RMS 15 cycles. We have 60 cycles coming out of the wall. That means you've got to measure the current for a quarter of a second for 15 cycles out of 60, 25% of it. And that's a running average. That's how it's done. The other thing they'll say, we have peak amperage. Well, as I can show you on the oscilloscope here, even with as dead short as we have on this transformer with a spot welding, okay, after we're done with the welding pulse, you will find that there's what's called ringing after it. It is at 1400 hertz. Well, if the length of this cable, which is 8 feet long, is 8.3 milliseconds, which is a half of a 60 cycle you know, that's one of the up skis or one of the down skis. All right, what they're talking about is narrower than that probe. I don't have anything on the table that's as narrow as 1400 hertz. I mean, it just, and so it just is not true. It's just not, it's not that it's untrue that they've got a peak current of something, but it's a useless piece of information. What we need to measure is true RMS over 15 cycles. If they're not doing that, they're just making up stories. And the number that they have is basically kind of interesting, curious information, but it's not something that's useful. All right, next thing I want to show you, I've showed you how to measure the current. I've showed you how to do this stuff. Next thing I'm going to do is I'm going to hook up my oscilloscope to the welder here, and I'm going to show you what phase shifting looks like on an oscilloscope. We've all seen 60 cycle hertz, and now what I'm going to show you that also. But then besides that, I'm going to show you what phase shifting looks like, and I'll be back just in a minute when we're done with this. Be right back. I've set up my oscilloscope again, and what I have is this oscilloscope going over here and picking up the line voltage. I have the other oscilloscope, because it's a dual trace scope, coming over here and picking up the secondary of the transformer. So we're going to see what's coming out of the transformer. And if you look here, I've got both signals on the display right now. And that line going across there indicates that there's no welding current going on. I can turn that line off, and now we just see the line current. You notice it's kind of a funny shape there. It's kind of got a little knock in it. And the reason for that is because this is 208 volt three-phase, and one of the sine waves is not perfectly on top of the other, so it kind of smooshes over the sine wave just a little bit. The transformer doesn't seem to mind very much. It doesn't mind at all. All right. If I turn that on, then they oscillate. If we put that like on, then they add together. Now I'm going to put the power on, and you can see as I adjust the power up and down. Now I'm going to turn off the other one. Now this, what you're seeing there is just the light bulbs. That's just the light bulbs going up and down. All right? And, oh, actually, I went in here, did that wrong. There's just the light bulbs going up and down. And it has a funny look to it, and the reason is because the look has this 50 pounds of iron that it goes out and excites, and if I were to disconnect the transformer itself, if I were to disconnect the transformer and just run the light bulbs, you would see that the sine wave would look different than it does. And what the sine wave would look like is much more like this here. That the, well, we just erase this here, we don't need this anymore. Alright. This is the zero crossing, alright? And this is the sine wave. Okay? And you can see that on the scope. Let me get a different color here. Let me get a red one. And when the zero crossing happens, what we do is we time from here, going this way, then we turn the power on, and it comes on like this. Now, if you're just exciting light bulbs, that's what it looks like. And this stuff here that I'm going to shade in red, that red stuff is what's called the true RMS power. And that's what the machines are capable of measuring. So anyway, that's what we're doing when we do what's called phase shifting. And we use SCRs to do that. And that's what the trick is there. It's not a big deal. Anyway, I just thought you'd be interested in seeing something like that, so that's why I did that for you. And so now you've seen that, and you're impressed with that. I have, let me unplug this stuff here. Put this to the side. Here's some other things that I wanted to show you quick like. Here's the here's the primary windings out of my transformer. There's 72 turns, and like I said before, it's number 8 square wire. The wire is actually square. You will also find this is the primary, or excuse me, this is the secondary, and you can see that this goes around and around and around, and when it comes to the front, we just ZD it and come around. There's 3 turns on here. What happens is you have 72 turns versus 3 turns, or a gear reduction of 24 to 1. And so if you have 240 volts in the wall, you get 10 volts out of the transformer. If you only got 208 volts, you get less. And we've already measured that there's less. Okay. This is the iron lamination. In familiar terms, we call it lamination, or we call it iron. And these are wasteless laminates. And they're made like this. And they take and they punch them out, and they look just like that. And I don't know if Kenny can get a great picture of that or not, but I think you can see what that looks like. There are 2 pieces, 2 E's facing each other, and the 2 I's go right here in the center. And this is one E, and this is the other E. And so they're wasteless. There's no waste to them. And all that happens is when we assemble the transformer, we stack up all the E's this way, like that, and we put the I's across the bottom like that, and that makes the windows of our transformer. The bigger that this is in here, the cross-sectional area, the more power it has. The longer the transformer gets, the more power it has. And the square area of this and the width determines how much power the transformer actually has. If you notice, the laminates have kind of a funny color to them, and that's because this steel is heat-treated. And they make this steel out of a very, very mild steel, and they can salt it or alloy it. Sometimes they use silicone, whatever. But the stuff is just dead soft. There's no strength to it whatsoever. It's just nothing. It's just nothing. And it's made that way so that it has really good magnetic characteristics, and being dead soft seems to do that. And that's how we make transformers. So I just thought maybe you'd be interested in seeing that. And they're just assembled, and when you see the transformer, you can see that there's some paper in there, and the paper is Nomex, and you can take a blowtorch to the Nomex, and it disturbs it, but it's a very, very high dielectric, and it's got good temperature characteristics, so over 800 degrees Fahrenheit. I mean, the varnish on here, the darker the varnish, the better the varnish. But this varnish is only good to, I forget what it is. I think it's 450 degrees centigrade, or Fahrenheit rather. So that's pretty much all that there is to it. You saw now what the sine wave looked like. You saw what the phase shifting looks like. You see what it does to light bulb. And it does the same thing to the welding power. You see how we measure this stuff. Actually, in industry, when we measure stuff, instead of using one of these, we use what's called a Rogowski coil. I don't even own one of those. They're about $1,700 for the coil, and you need a special meter reader. It's about $3,500. The equipment that I have is more than accurate enough of what I'm doing. You can see what's happening. You can hook your scope to it. There's ways to hook your scope through this thing, and you can see the secondary, and so on and so forth. There's a lot of different things you can do, and I do those because when you design the transformers and you design the circuitry that controls them, and so you can get the maximum and minimum and where you can set the power. That's all important to me. And then I just simply sell the machine to you, and then you get on with the rest of your life. So anyway, I think that pretty much covers that. Otherwise, I'll go on forever and tell you car stories. And I hope you've enjoyed watching the program. I put a lot of work into it, and I think it's a nice program. I want you to remember that I have an 800 number. If you ever got a problem, you can call me. My 800 number is 800-666-2358. If you got a problem with the welder, you're wondering what's happening, you give me a call. As long as I've been selling these things, I'm pretty sure that I've figured out most all of the problems. I'm not sure I've figured out everyone, but it's been several years since I found the question difficult to answer. Anyway, enjoy your new welder. Practice with it before you take it out in the shop and start to use it for a real tool. The few minutes that you spend fooling around with it, playing with it, and figuring out how it works and how to set the knobs and adjust it will pay you many, many, many hours of dividends in time saving once you get to learn how to use the machine. Practice with the 2 gun before you take it to a car and use it on a car. Practice with the 1 gun. Practice with the nails on junk that you're going to throw away. Figure out where the knobs are set in your shop. Practice with the pliers. Figure out what it needs. And, you know, I've gone over all of that stuff already. Use plenty of air on the tool. If you don't use air on the air tool, it's the only thing that will damage it. The air cooling actually goes in here, and because it's cooling in here, it starts to cool on the transformer. Oh, one other incidental item. It just reminded me. Some of my competitors, when they tell you how to measure or where to measure the secondary voltage, like on this board back here, they're going to tell you that you would measure it down here. That is categorically untrue. If you were to measure it down here, that would be to say that there's no loss in these cables and they don't get hot, but indeed they do get hot. You have to measure the voltage across here. I can cheat. You know, if I went down and measured this stuff here, I could probably crank out 50,000 amps. Well, it would be a lie, but unless somebody tells you how you measure this stuff, then you don't know how to do it. And everything from here on the transformer is resistance. This piece of bar stock, all of the cable, all of the pliers, everything has resistance in it. And that's the loss. And if you're wondering why we don't make the cables 25 feet long, it's because you need a lot bigger motor back here so you can tolerate the loss in the cables going to the welding pliers. And you just need an enormous transformer because you're going to have bigger losses and you're going to have to dissipate a lot more heat. Anyway, so I think I've pretty well covered everything I want to cover today. And you have a good time with your new machine. And if you need something, give me a ring. And thank you very much for your patience and your energy. Thank you. Bye-bye.